In the silent depths of space, among billions of stars, visits still occur that leave humanity breathless with wonder. One such guest is 3I Atlas, a new wanderer that burst into our solar system like a message from another stellar era. At first, it was noticed as a tiny speck, barely distinguishable against the backdrop of distant galaxies, but it soon became clear. This was not just another comet. Its speed, direction, and behavior didn't fit any familiar description. Scientists were immediately intrigued. The object's orbit suggested it originated not from the depths of the Oort cloud, where typical comets are born, but from interstellar space, beyond everything we call our system. 3I Atlas's velocity was higher than most bodies orbiting the Sun, making it clear that it couldn't be captured by gravity. It would simply fly by, leaving behind only a mystery and a trace in instrument data. But as soon as the news appeared in scientific databases, a storm of speculation, sensationalism, and alarming headlines erupted. The internet buzzed. Some called it the second ʻOumuamua. Others insisted it behaved unlike a comet, and some even declared it a probe sent by an intelligent civilization. Scientific forums filled with discussions, while popular videos featured alarming phrases like, "It's approaching Earth," or "Scientists are hiding the truth about 3I Atlas." Meanwhile, astronomers tried to remain level-headed. After all, this was already the third confirmed interstellar object to visit us. The first was ʻOumuamua, discovered in 2017, elongated, shining, like a cosmic fragment or something crafted by an engineer. The second was Comet Borisov, whose appearance in 2019 proved that interstellar wanderers are not a myth but a reality. Now, 3I Atlas has become the third in this short but historic list, continuing the chain of mysterious visits from beyond our galactic neighborhood. Each such discovery is like a letter from an unknown world. It brings not only new data but also new questions. Why are these objects appearing more frequently? What do they carry with them? Just ice and dust? Or fragments of alien worlds? And perhaps a hint that we are not alone in this stellar darkness. 3I Atlas has become precisely such a reminder. The cosmos is alive, and it responds if we know how to listen. When we talk about 3I Atlas, we cannot overlook its speed, precisely what initially caught astronomers' attention. At first glance, 60 kilometers per second seems incredible, especially for an object merely passing through our solar system. But upon closer examination, this unusualness takes on clearer contours. To begin, let's recall, before 3I Atlas, humanity knew of only two interstellar visitors, ʻOumuamua and Comet Borisov. Their speeds upon entering the solar system were approximately 25 to 30 km/s. This was considered natural. Stars around us move at similar speeds, and the Sun, along with its planets, orbits within the galactic disk at an average speed of about 200 to 20 km/s. However, this doesn't mean all objects within the disk move relative to each other at the same velocity. Young stars, recently formed from relatively calm gas clouds, pass by at low speeds, around 10 km/s. Stars like the Sun, of medium maturity, have characteristic speeds of 30 to 35 km/s. Meanwhile, old stars, which formed long before the Sun, sometimes reach speeds of 250 km/s. Against this backdrop, 3I Atlas's speed, about 58 to 60 km/s, indeed stands out among the three known interstellar guests, making it the speed champion. But how far does this deviate from the natural? Actually, not critically at all. To better understand, imagine a highway with cars. Most are driving at roughly the same speed, but some are slightly ahead, others lagging behind. The average speed is a reference point, but individual participants can significantly exceed or fall short of it. 3I Atlas is like a sports car among ordinary vehicles. It's faster, but still within the bounds of what nature allows. Thus, The high speed of 3I Atlas is an interesting feature, but not a universal sensation. It merely underscores how diverse the objects capable of traveling between stars are. And although catching such a cosmic speedster with modern spacecraft is nearly impossible, its study remains a crucial task. Every flyby opens new opportunities for understanding interstellar space and galactic dynamics. Moving beyond the discussion of 3I Atlas's speed, a natural question arises. Where did this mysterious visitor come from? Like its predecessors, ʻOumuamua and Comet Borisov, it arrived from distant regions of the galaxy, but its exact system of origin cannot yet be identified. Scientists turned to stellar dynamics to attempt to trace its path back in time. Using precise data on the motion of nearby stars and modeling their orbits tens of millions of years into the past, astronomers were able to reconstruct the trajectory of 3I Atlas. The modeling shows that the object traveled through interstellar space without approaching any known stars. It seemed to cross an empty galactic abyss, without a fixed home. This picture demonstrates the complexity of the task, even knowing the object's speed and direction of motion. It's impossible to definitively determine which star system released it. The absence of close encounters with neighboring stars rules out simple explanations and underscores that 3I Atlas is a true interstellar wanderer. The conclusion is simple, yet intriguing. Despite our ability to track the movements of numerous stars and objects in our galaxy, some guests still appear out of nowhere, remaining a mystery. 3I Atlas did not pass near any known star, and therefore, its origin remains an enigma. And this enigma only adds to the allure of observing it, turning every new image and calculation into an important fragment of an interstellar detective story. After tracing the path of 3I Atlas through the depths of the galaxy and confirming it didn't pass close to any known stars, its journey brings it into the solar system, and here the object becomes particularly interesting for observers. The orbit of 3I Atlas almost coincides with the plane of the ecliptic, deviating by only 5 degrees from the trajectory of Earth and other planets. Such a small inclination is likely coincidental, but it makes close approaches with planets more noticeable and convenient for study. The object will first encounter Mars on October 3rd, passing relatively close to the planet. At this moment, Martian orbiters, like the Mars Reconnaissance Orbiter, will be able to use their telescopes and cameras for observations and potentially for analyzing the object's composition. Next, ʻAtlas will approach the Sun, reaching its closest point, similar to Earth's distance from the Sun, on October 29th. Observing it from Earth will be difficult. The Sun will be positioned between us and the object, its glare overwhelming the view. However, on December 19th, the object will make its closest pass relative to our planet. The distance is still vast, but it will provide an opportunity for orbital telescopes, including the James Webb, to study its chemical composition and dynamics. From a gravitational perspective, March 2026 will be significant when 3I Atlas passes near Jupiter. The planet's enormous mass could slightly alter the object's trajectory, changing its subsequent flight out of the solar system. This maneuver, a natural interaction with a massive planet, will allow the object to continue its journey at nearly the same speed it arrived with, around 60 kilometers. Thus, each encounter with the planets of the solar system is not just a coincidence, but an opportunity for scientists to study a unique interstellar object. Mars will be the first observation station, the Sun will test our observational capabilities, and the interaction with Jupiter will demonstrate the influence of gravitational giants on the flight of cosmic visitors from distant systems. 3I Atlas continues to remind us that interstellar objects can provide unique research opportunities if we spot them in time and prepare appropriately. After 3I Atlas passed Mars and headed toward the inner solar system, interest in it among scientists and astronomy enthusiasts only intensified. Its behavior, stable yet somewhat peculiar, reignited an old debate. Is it just an ordinary comet or something more? Bold theories emerged immediately after the initial observations. Some enthusiasts began talking about a disguised alien spacecraft, a hypothetical probe using a comet-like appearance to avoid suspicion. Such speculations always accompany rare interstellar visitors. Their mysterious origin, unusual trajectory, and lack of precise data make them perfect fodder for imagination. However, astronomers, relying on physics and observations, lean toward a more natural explanation. Yes, 3I Atlas doesn't behave exactly like a typical comet, but that doesn't make it a technological artifact. Spectral studies revealed that as the object approaches the Sun, it primarily releases carbon dioxide, CO2, rather than water, unlike most comets born within our system. This fact could be the key to its true nature. This behavior suggests that 3I Atlas formed under unusually cold conditions, perhaps in the outskirts of a distant planetary system where water ice was too solid, while frozen CO2, evaporating first, created the characteristic smoking effect. There, on the boundary of eternal cold and interstellar darkness, this frozen oddity might have been born before being ejected beyond its native sun. And although the probability of an artificial origin is minimal, the very fact that it's being discussed speaks to something else: our readiness to seek out and notice the unusual. 3I Atlas is like a mirror. It reflects both our scientific knowledge and our dreams of extraterrestrial civilizations. We don't know who sent it on its journey, nature or intelligence, but its presence reminds us that even interstellar wanderers can carry answers to questions humanity has been asking itself for thousands of years. After all the hypotheses about the nature of 3I Atlas, whether it's a comet, a fragment of a distant system, or even a technological messenger, scientists face a more down-to-earth, yet equally complex question. How do we even study such objects when they fly through the solar system with near-cosmic swiftness? 3I Atlas, like its predecessors ʻOumuamua and Borisov, moves at a colossal speed, tens of kilometers per second. This means that only a few months pass from the moment of its discovery to its closest approach to Earth. For space missions, this is catastrophically short. Even the fastest probes like Parker or New Horizons simply wouldn't have time to turn around and intercept it. To organize a rendezvous, we would need to know about the visit long before it becomes visible to telescopes. This problem has given rise to a new idea: the concept of interceptor spacecraft. Scientists and engineers at NASA and ESA are increasingly discussing the creation of small automated probes that would wait in orbit in a standby state. Their task would be to launch instantly upon receiving a signal about a new interstellar object whose trajectory crosses the inner solar system. Such spacecraft could catch up with the visitor, take photographs, measure its composition, and even deploy a mini-probe to collect particles. It sounds like science fiction, but such a strategy could become a reality within the coming decades. However, for such a system to work, one thing is needed: prediction. Astronomers must learn to calculate the potential trajectories of interstellar bodies before they approach. This requires constant monitoring of near-solar space using sensitive telescopes and automated algorithms, capable of detecting the slightest anomalous movements among millions of stars. San Faternein for on Theater has once again served as a reminder. The cosmos is full of visitors, but if we want to meet them face to face, we must learn to be prepared. After all, interstellar wanderers don't wait. They fly by, carrying with them secrets of other worlds, and it's up to us whether we can one day not just observe them, but reach out a hand in greeting. After discussing the difficulties scientists face when trying to study interstellar objects, a logical question arises. Why have we only begun finding them so recently? The cosmos hasn't suddenly become more generous with visitors from other star systems. It's simply that humanity has finally learned to see what previously went unnoticed. Just 20 years ago, celestial mechanics and the search for comets and asteroids were the domain of individual observatories where observations were conducted manually or with minimal automation. Back then, even bright objects could escape notice simply because the sky is too vast and human attention is limited. But in recent years, a technological leap has literally revolutionized the capabilities of astronomy. Robotic telescopes have taken center stage, intelligent systems that scan the sky around the clock, searching for moving points of light. They can analyze millions of images per night, instantly calculate trajectories, and report any anomalies. It is precisely such systems as Pan-STARRS, Atlas, and ZTF that gifted us ʻOumuamua, Borisov, and now 3I Atlas. Each new instrument discovers more than entire generations of past observers. Ironically, the Chelyabinsk meteor, which entered Earth's atmosphere in February 2013, served as a catalyst for these achievements. Its sudden appearance and powerful explosion were an alarm signal for the scientific community and governments. The sky demands attention. This incident triggered a new wave of investment in near-Earth object observation programs, accelerating the development of automated detection technologies. Since then, space surveillance has transformed from an academic interest into an element of planetary security. Modern cameras, equipped with sensitive CCD sensors and artificial intelligence systems, detect the slightest movements of stars and asteroids. Every month, catalogs are updated with up to 1 million new objects, from unnamed rocks to entire comet families. In this ocean of information, special attention is given to bodies with unusual orbits, those whose trajectories suggest not an internal origin, but a visit from interstellar space. This is why discoveries like 3I Atlas have ceased to be sensations and are instead becoming the beginning of a new era. Astronomers are convinced that in the coming years, we will find dozens, if not hundreds, of similar visitors. Perhaps some will be accompanied by dusty tails, others by cold, rocky nuclei, and yet others by enigmatic trajectories that defy conventional models. Humanity has finally ceased to be blind within its own system. We have learned to gaze into the darkness, and it has begun to respond. After humanity finally learned to detect the tiny wanderers traveling between stars, the first true interstellar visitor did not keep us waiting. In the autumn of 2017, an object entered the lenses of the University of Hawaii's telescopes that would change our understanding of what could be hidden in the cold depths of space. It was named ʻOumuamua, from the Hawaiian for a messenger from afar arriving first. It entered the solar system at an incredible speed, and at such a strange angle that it was immediately clear. It was not from here. But the most astonishing thing wasn't that. It was its shape. Observations showed. The body rotated unevenly, reflected light unpredictably, and from the intensity of its glints, one could only guess that it was elongated, perhaps stretched out like a cigar, or conversely, thin and flat like a disk shimmering in the sunlight. This anomaly sparked a wave of speculation. Some scientists cautiously spoke of an unusual asteroid fragment, others, a piece of a shattered planet. And the internet instantly latched onto a more sensational version. It's an alien spacecraft. After all, ʻOumuamua not only moved strangely, but also appeared to accelerate, even though no tail or signs of outgassing were visible in the images. However, as is often the case, the explanation turned out to be less sensational but far more elegant. Subsequent research showed the acceleration could be explained by the sublimation of nitrogen, a substance that turns directly from solid to gas when heated, even by weak sunlight. If ʻOumuamua was indeed composed largely of frozen nitrogen, it could have been a fragment from a distant exoplanet covered in nitrogen ice, similar to Pluto. Under the influence of stellar wind, this ice gradually evaporated, creating a barely noticeable gas pressure, just enough to gently push the object forward. Thus, the hypothetical alien probe, ʻOumuamua, transformed into an example of how nature can create forms no less astonishing than any technology. Its story became a symbol of the cautious scientific approach, a reminder that even the strangest phenomena have natural explanations, if we observe long and carefully enough. ʻOumuamua became for humanity not just the first interstellar guest, but also a sign that our galaxy is alive, full of travelers journeying between worlds for millions of years. And somewhere among these travelers, new ones are already approaching, like Borisov and 3I Atlas, carrying their own secrets and new questions. Just as we were growing accustomed to the idea that secret visitors from the depths of the galaxy could appear in near-Earth space, another, more down-to-earth story emerged in the media sphere. A video from China showing something falling through the atmosphere and then, it seems, meeting its demise. This episode quickly became a subject of debate. What exactly is shown in the footage? A natural bolide, a defunct artificial satellite, or the result of an anti-satellite weapon test? The video shows a bright dot moving across the sky at an angle to the Earth's surface. A glowing trail follows it, and then a second dot appears, rapidly catching up to the first. Soon after, a flash and a cloud of light. Such footage can be interpreted in various ways. A meteoroid entering the atmosphere often breaks apart and can produce a similar visual. A decommissioned satellite can also begin to disintegrate upon re-entry, creating fragments and sparkling glow. But what's unusual in this clip is precisely the encounter moment. Something, presumably launched from the ground, overtakes the target and is followed by an explosion. This gave rise to the version of an anti-satellite exercise. Many countries possessing space systems and defense technologies periodically conduct tests simulating the destruction of an object in orbit. Such maneuvers use kinetic impact, as well as modules that disable the craft, or directed energy effects leading to its destruction. A test might look exactly like this: an object on an intercept trajectory, followed by a rapid interception and a bright detonation. Of course, no official confirmation regarding this specific video followed. Government agencies often do not comment or provide limited information about such operations. An alternative, more prosaic hypothesis is that it was an old satellite spontaneously re-entering the atmosphere and disintegrating. Spacecraft that have outlived their usefulness lose altitude, and upon entering the denser layers of the atmosphere, experience aerodynamic and thermal stresses. Broken-off pieces fly separately, creating the impression of the object being sliced and subsequent debris scattering. This is often what the re-entry of space debris looks like. Another possibility is a meteoroid that, upon atmospheric entry, breaks apart and explodes. Sometimes fragments are visible around the event site, flying in different directions. Finally, a logical assumption is the testing of an anti-air or anti-satellite weapon, where the target is not a natural object but an old satellite deliberately placed on a controlled trajectory. This is practiced. It's better to destroy a redundant craft than to risk an uncontrolled fall. The video does indeed resemble footage from such tests. The characteristic meeting of two dots, a sharp flash, subsequent light diffusion. But without official information, any conclusions remain speculative. The significance of this story isn't just that we saw footage of some catastrophe. What's important is something else. It highlights how our sky has become congested with both human-made and natural objects, and how thin the line is between the natural and the artificial. We've already discussed how a random bolide prompted a reassessment of near-Earth space observation priorities, and now here is another signal. Orbital control, disposal of old spacecraft, and the development of anti-satellite capabilities affect what we see in the sky. This is another reason why astronomers, engineers, and policymakers must act in concert. to distinguish scientific sensations from military operations, natural events from human-made threats, and to minimize accidental risks for people on the ground. In any case, this fragment served as a reminder that the boundary between space science and geopolitics is becoming increasingly thin, and every striking piece of footage from the heavens is now scrutinized not only in scientific journals, but also in military briefings. After the story of the Chinese video and the speculation about the nature of mysterious flashes in the sky, humanity was reminded once again. Space not only beckons, but also threatens. Where we see mysterious lights and flying objects, a real problem lurks: the danger of collisions. And while comets like 3I Atlas will pass us by, other, far less harmless objects may one day find themselves on a trajectory leading straight to Earth. The scenario of a large asteroid impact is not a fantasy from movies, but a mathematically probable event. Our planet's history knows examples. The Chicxulub impact that wiped out the dinosaurs, the Tunguska event, the Chelyabinsk meteor, all are links in the same chain. This is precisely why, in recent years, the efforts of astronomers and engineers have increasingly focused not only on observation, but also on defense. We are talking about real planetary protection. The main idea is simple: to learn not just to predict, but to deflect potentially hazardous objects. And in 2022, humanity made the first transition from theory to practice. NASA launched the DART mission, the Double Asteroid Redirection Test. A small spacecraft, the size of a car, was sent to the binary asteroid system Didymos, more precisely, to its moonlet Dimorphos. The goal: to collide with it at a speed of over 6 kilometers per second and test whether such an impact could alter its orbit. The collision scene itself looked like a frame from a science fiction movie. DART's camera transmitted its final images seconds before impact. The asteroid's surface approaching, large boulders, shadows, and an instantaneous flash. The signal was lost. Then, after days of observations from Earth, confirmation came. Dimorphos's orbit had indeed changed. Moreover, the effect was twice as strong as calculations had predicted. The reason? A jet of ejected debris. When the spacecraft struck the asteroid, some material was thrown outward like a gas jet, acting as an additional engine. This not only proved the method's effectiveness, but also showed that even a small craft, properly directed, can alter the fate of a kilometer-sized body. Now, DART is not just an experiment, but the starting point of a new era in space security. It will be followed by missions like ESA's Hera and others, which will study the impact's aftermath, the crater's structure, and the dynamics of the material ejection. Scientists are already modeling scenarios where such spacecraft operate not alone, but in groups, intercepting threatening asteroids well in advance, long before any potential impact. This experience has given humanity the most important thing: confidence. For the first time, we proved that we can influence the orbit of a celestial body, however small. And although the path to reliable Earth protection is still long, it is now clear, when the next stone from the abyss appears on the horizon, we will have not only the time to spot it, but also the means to change its course. And perhaps this is the best outcome of all our observations, anxieties, and experiments. For true mastery in space exploration begins not with conquering planets, but with the ability to protect our own home. After the planetary defense missions, humanity seemed to find a new lease on life. We learned not only to deflect external threats, but also to gaze into the depths of space with unprecedented clarity. If survival was once the primary goal, now it is understanding. And the primary tool of this new stage of exploration has become the James Webb Space Telescope, the most powerful observation machine ever created by humankind. This giant, shielded with gold-coated mirrors, operates not merely as humanity's eye, it has become its memory and hope. Since its deployment, Webb has been studying everything, from early galaxies born shortly after the Big Bang to dusty rings within our own solar system. Every pixel of its images is a step toward answering the question humanity has asked itself for millennia. Are we alone in the universe? One of the telescope's most important targets became the TRAPPIST-1 system, a tiny, cool star orbited by 7 rocky worlds resembling Earth. The planet TRAPPIST-1e is particularly intriguing. In size and mass, it is almost identical to our own, and its distance from its star is such that liquid water could exist on its surface. Such objects have become prime candidates in the search for life beyond our solar system. To determine whether TRAPPIST-1e truly has an atmosphere, Webb uses the method of differential observations. When the planet transits in front of its star, some of the starlight filters through its atmosphere. If certain chemical signatures, such as methane, oxygen, or water vapor, are present in this light, it could mean there is more there than just a rocky world. It's like listening to the breath of a distant planet, catching familiar rhythms within it. The results are only just beginning to arrive, but even the initial data is astounding. The telescope detects minute differences in the light spectrum, hinting at the possible presence of dense atmospheres around some of the TRAPPIST-1 worlds. This is not direct proof of life, but it is the foundation upon which one of humanity's greatest discoveries may one day be built. Every new image, every spectral line sent by Webb from the cold Lagrange point L2 seems to expand the boundaries of the possible. We are seeing worlds that, until recently, were mere hypotheses. We are learning to recognize the signatures of carbon and oxygen where no human foot has ever trod. And perhaps, within the coming decades, it will be this telescope that first shows us not just a distant planet, but an alien world upon which something breathes. Thus, the journey from fearing space to marveling at it is complete. From attempts to defend ourselves to the striving to understand. Atlas, ʻOumuamua, Borisov, DART, and now the James Webb Space Telescope. These are links in the same chain, symbols of the evolution of humanity's perspective on the universe. We no longer await an encounter with the unknown, we actively seek it. And perhaps, when Webb one day detects a faint trace of a biosignature from a distant star, it will mark the beginning of a new era. An era in which humanity ceases to be a spectator and becomes part of the grand cosmic story.